Next, we discuss the apparent power. For such a one-port network containing RLC and dependent sources, we can use a serial connection of a resistance and a reactance to represent it. That is, for such a circuit, we have the impedance triangle, where phi is the impedance angle. Similar to the impedance triangle, we have voltage triangle. Here phi is the angle of phase difference between voltage and current seen from the port. It can also be the impedance angle. We define P equals Ui cosine phi in lecture 66. We just defined Q equals Ui sine phi. Here the phi is both the impedance angle and the phase difference of the port voltage and the current. So we can draw a power triangle naturally, that is, we define the hypotenuse of the apparent power S, and its unit is VA. So why do we define the apparent power? The apparent power is used to represent the ability of providing power of the power supplies. You can see directly through the discussion in the next slide. It's the inductive power. We assume that the effective value of the power voltage is 10 volts. We also assume that the load always absorbs power 10 volts. Let's have a look at the values of current under different power factor. They meet the relationship of P equals Ui cosine phi. For the case that the power factor is equal to 1, it's easy to calculate that the current is 1 ampere. If the power factor is 0.5, then the current must be 2 amperes. If the power factor is 0.1, the current must be 10 amperes. Do you find? The power factor of the load will directly determine the value of the load current delivered by the power supply. For the power supply, its port voltage needs to be kept as 10 volts. It needs to provide different current under different power factor. So we define that the apparent power is the product of voltage and current from the power supply side. That is to say, apparent power S represents the capability of providing power of power supplies. The greater the ability is, the greater the capability of sustaining the load with small power factor is. Through the discussion, we can find that the small power factor is unfavorable for the whole circuit. On the one hand, we waste a lot of power on the source. On the other hand, larger and larger current produce more and more loss on the transmission line. It's unfavorable for the circuit. So it's very necessary to increase the power factor seen from the source side. So how to do? Remember the example discussed in lecture 66? After an inductive load connected a capacitor in parallel, the power factor seen from the power supply side is increased. Here we use a phasor graph to analyze this process. Suppose the port voltage U as a reference vector. Because the load is inductive, so IL must lag U. For capacitors, the current leads voltage 90 degrees, so the direction of the capacitive current is vertical upward. We use KCL for the node and draw the phasor graph by the method of head-tail connection. That is, the starting part of the IC is the end part of IL, so we can get, and the total current is like this. We might as well define that the power factor angle before compensation is phi 1 and the power factor after compensation is phi 2. You can see that the power factor angle is decreased after connected with the capacitor, so power factor is increased. In addition, it's important that because the load power is Ui cosine phi, that is to say the projection of the current on the horizontal axis determines the load power. So after connected with the capacitor, it will not affect the active power of the load. Of course, different capacitance value can provide different compensation power factor angle. For example, we can choose the capacitance to make the voltage and current in phase seen from the port. In this case, all the power supplied by the source is the active power of the load. Again, for instance, we can also choose a capacitance to make the power factor angle change from phi1 lag to phi2 lead. But it should be noted that we often use such a way for increasing the power factor. That is, we choose a capacitance to make the power factor angle still lagging rather than compensate to the state of resistive or capacitive. Why? There are two reasons for this. The first is the cost of the capacitors. With the increase of compensation capacitive current, the number of capacitors needs to be increased, so the cost of the compensation increases. In addition, if the current seen from the port compensated is capacitive, then the current might be resonant and produce bad effects. We will discuss about the resonance in lecture 72. Why is it unfavorable for the compensation for the resistive state? That's because the work of the actual circuit is not as we imagined, static and constant. The connection and disconnection of the load is random. That is to say, the active power of the load probably changes over time. During certain time period, if the power factor angle seen from the port is compensated into zero, then sometimes it's likely to be changed into capacitive and it might be resonant. These are two main reasons why we adopt this compensation again.